Good evening to everyone present here and everyone joining us through the live stream. I, Uday, along with my co-hosts Devangi and Shambhavi, welcome you to Particle Physics Demystified, a unique session centered on this fascinating part of physics organized by Team Nucleus. We also welcome our honorable guest, Mr. Matthew Ivalich, the head of Connected Learning at Shivnada School, Noida, and also our honorable speakers, Dr. Kenvi Nishiwaki and Dr. Arindam Chatterjee. I would now like to hand it over to Shambhavi to introduce the event to you.
Shambhavi, are you speaking?
No, not only is the universe, it is stranger than we can.
Okay, Shambhavi, we cannot hear you. We cannot hear you. Can you please repeat from beginning? Or if there is a technical problem, yeah, please be loud and please introduce once again.
Hello?
Yeah, please go ahead.
Can you hear me now? Hello?
Yes, Shambhavi, you can go ahead.
Okay. Fine. So, not only is the universe stranger than we think, it is we can.
No, we cannot hear you
Take
properly.
you through the journey of understanding the particle physics.
May I request Devangi or Uday to start video, switch on the video and speak? Shambhavi, we are sorry, bache, we can't hear you. So please go ahead, Uday. We'll see when Shambhavi fix up her audio, then she will come back at end. Uday.
All right. All right. So welcome everyone once again. This session will take you through the journey of understanding particle physics, which is simply what you, I, the sun, and the galaxies in the universe are made of. The Team Nucleus feels privileged to welcome Dr. Arindam Chatterjee, assistant professor in Department of Physics at Shivnada University, and Dr. Kenvi Nishiwaki, also assistant professor in the Department of Physics at Shivnada University. Dr. Arindam did his bachelor's from the Chennai Mathematical Institute in India and his master's from McMaster University in Canada. He was a postdoctoral fellow in Harish Chandra Research Institute at Prayagraj. His research interests lie broadly within theoretical particle physics, astroparticle physics, and cosmology, and more specifically in dark matter and inflationary cosmology and the aftermath. He was selected for the DST Inspire Faculty Fellowship in 2015. Dr. Kenji did his bachelor's and master's from Kobe University in Japan. He was the cooperative postdoc researcher in the Department of Physics at Kobe University. He has also been a research fellow in the Korean Institute for Advanced Study. He has also worked as a postdoctoral fellow in the Division of Theoretical Physics, the Rudyard Boskovic Institute in Croatia. His research interest lies in particle physics, phenomenology, and he is a member of the New Higgs Working Group in Osaka University. We are thankful for the presence of both of you, and we thank you for sharing your valuable time to quench the thirst of knowledge of all our attendees here and on YouTube. We hope that this session brings something new to the audience, and many of you feel inspired to explore this part of physics. The audience present on YouTube is welcome to share all their questions live on the YouTube stream so we can take them up later. And we also request you to stay until the end for an exciting announcement about a new program that Nucleus plans to launch soon. Now, before we begin the question answer session of the event, I would now like to invite Mr. Matthew to share a few words with us.
Well, good evening, everyone. How exciting to be connected again. I'm so happy because I see our students hosting. I see the eminent professors that have just been read out as part of our connected community at Shivnada School. It's not every school that gets the quality of academics we're about to listen to. It's not every school that has a Miss Vanita and the Nucleus team who bring this together. I hope that everyone treasures these moments, that they are vocal in their questions, that they explore things that can be demystified. I know this session is so interesting when we talk about the new particles and the forces of the universe. So please explore. Please look at this. As I've always said many times on these sessions, we're not in the classroom. We are in the classroom of the future, but we're living it now. We are in so many different places in a geographical sense around our country and around the world that we can actually come together and connect. So let's learn more, let's enjoy our learning, and let's continue that passion in physics and learning in general. So welcome to you all tonight. Do stay connected and do stay with the program that Miss Vanita has set up, because this and many more sessions will only enlighten your understanding and I hope your passion for learning. Thank you, everyone. Have a good session.
Thank you so much, Matthew, sir. Your words never fail to inspire us. Now I would like to kickstart the event by asking the first question, and hopefully this will set the stage for a lot of inquiry in the field of particle physics. Now, the first question is posed to Dr. Arindam, and I want to ask that we have come across the idea of particles in various contexts, and the idea of everything in the universe being composed of these fundamental particles is surely very intriguing. Can you please tell us about what really these fundamental particles are and why do we study them in particle physics?
Hi. Yeah, thanks, Uday, for the organization and, of course, the other organizers for the organization and the opportunity to share some excitement in particle physics as well as astroparticle physics in this webinar, or rather informal discussion. So let me try to answer the question that Uday has posed. But let me share the screen first. We managed to make some slides. So is the screen visible?
Yes.
Okay, thank you. Okay. So as the question already points out, so here is a version that Uday has already sent us before. So the idea of everything in the universe being composed of particles is surely very intriguing. So can we talk about what really these fundamental particles are and why do we study them in particle physics? As for why, the answer is a bit simpler. It's in basic science, research is mostly curiosity driven. It's driven by our thirst to know more and more about nature, learn and understand. The question that you were asking today was also asked long ago by Greek philosophers, Indian philosophers, Chinese philosophers, what are we made of? And they came up with different models like the air, earth, fire, that kind of stuff, like five of them, and so on. And of course, with the advancement of science and technology, today I would briefly share where we stand today as for our understanding of this question. Okay. So the particle physics is going to like smaller and smaller length scales and higher energy scales. So when we are trying to probe matter at smaller and smaller length scales, we need to go to higher and higher energy scales. So this is why particle physics or high energy physics, they go by about the same name. Here is a rough idea of the length scales, that order of magnitude. So as we know that 1 meter is roughly the size of a person, then a micrometer is roughly size of cells, and then atomic scales are, we know, size of hydrogen atom. This is about 10^9 meter or so, and atomic nuclei is about 10 power minus 9 meters. Here is 10 power minus 15 meters for atomic nuclei. So you see that most parts inside the atom is actually free. Sorry, there is some ambient background. If you could mute your mic. And then as we increase the energy, we go to smaller and smaller length scales, probing the smallest pieces of the what makes us the matter. And here, as we know, in high school, of course, we have learned that atom is made of a nuclei and then electrons are orbiting around it. And we study probably a bit about the Bohr atom model, which is not very accurate, but does the job. Then, of course, there is atomic nuclei. Nuclei, we know, is made of proton and neutron. And probably some of us have also heard of like protons and neutrons are made of something called quarks. Now, next question should be then in this order what the quarks are made of. And so far as we understand today, nothing. They are really, really fundamental particles. So here is a list of the fundamental particles that we know as of today. This fundamental in the sense that they are not made of anything. And I will briefly also sketch like how we know that something is made of anything. You have read of Rutherford scattering and experiments like that in the high school, read about that, right? So one way to know if something is made up of something else is just to bombard it with very high energy particles. For example, if you have a cold nuclei, you could shoot it with some alpha particles and then try to see the scattering. How is it deflecting? Yeah, so that's what Rutherford did, if I remember correctly. So anyway, so this is what the strategy is pretty much similar, although as I say that as we go to smaller and smaller length scale, subnuclear length scale, we need to go to higher and higher energy to do the same kind of probe of the constituents. So here, so these are fundamental particles, fundamental in the sense, so far as we know, today they are not made of anything else. This pink sector here, image is taken from Wikipedia. Pink sector is quarks. Each quark comes in 3 colors. It should not be confused with the usual colors that we see, but it's some kind of quantum number per se. So this is up, down, charm, strange, and top and bottom quark. And then the green section is leptons. So electron, neutrino, mu1, neutrino, tau1 and tau1 neutrino. And this reddish section is gauge bosons. They are kind of the force mediators, if you might say. All the quarks and leptons are spin half particles. So spin is another quantum number. This is, again, not something that is really spinning. So a particle, we are labeling simply using its mass, that is rest mass, and charge and spin. So here, these are the gauge bosons. Gluon is the boson for the strong force that holds protons and nuclei and neutrons together, for example. And then there is photon is the carrier for the electromagnetic force, and Z and W bosons are there are three of there are 2 W bosons. So W plus minus and then Z, these 3 together form the carriers of so-called weak force. And this is the most recent addition to the list. As you know that this is the Higgs boson. In 2012 it was discovered. Dr. Kenji Nishiwaki will elaborate more on the standard model of particle physics. But these are the particle contents that we know and as fundamental particle as of today. Now, as I said, the quest is to go to probe length scales of smaller and smaller length scales. We need to go to higher and higher energies, right? So in future, if we can make progress in the energy frontier, it is very much possible that newer particles will add up in the list. This is possible, but so far we do not know of any other members in this. Okay, so as I said already, that these particles interact among themselves, and there are 3 kinds of interactions here. That is a strong interaction, weak interaction, and electromagnetic interaction. Now, this weak and electromagnetic interaction can be, in a way, thought of as coming from same some sort of a basic interaction that goes by the name of electroweak theory, electroweak interaction. Okay. So, as I said, that interactions are mediated by the bosons, and then all these quarks and leptons, they have they participate in these interactions, right? So what does these interactions do? Interactions can change one type of particle to another. I would explain what this change is. And it can also lead to decay of the particles, although these particles are not made of anything more fundamental than but they can simply disappear. Actually, most of them that you see here do decay. So let us go to the next slide. So the particle content, the quantum charges, the quantum numbers that are associated to the particles, technically speaking, the gauge group, and under the gauge group, what are the charges these particles have. So you can take a simple example like electromagnetism, right? We know what the charge of electron is. It's minus E, mod E being the, let's say, the electron charge. Mu1 has exactly the same charge as electron. Tau1 also has the same charge as electron. Okay, the other gauge groups that we are talking about are similar to this one, basically, but let us ignore the technicalities. What I would like to say is that given the particle contents and the charge specifying the charge, one can write down a model of what kind of interactions would be allowed and what are not allowed. This model goes by the name of a standard model of particle physics. This standard models explains all the small scale phenomena in the realm of particle physics that we see up to about several hundreds of giga electron volt of energy. Up to that range, we know that this model pretty accurately explains everything that we are experimentally doing. Okay. Several prominent physicists contributed to building up the standard model of particle physics as we know of today. Is Tomonaga, Swinger, Feynman for quantum electrodynamics. So you have read about electrostatics and magnetism in classical physics in the class 2. So this is quantum electrodynamics is the theory for is the quantum theory for the electromagnetism. And then Glasgow, Salam, and Weinberg, again Nobel Prize for electroweak theory. That is their model unified the electromagnetic and weak interaction together. They put in a common framework, understanding from simpler assumptions. And then there is Gell-Mann, who proposed the quark model, one of the proponents of quark model. The list goes on. Of course, Peter Higgs, Francois Englert, they proposed the Higgs mechanism with several other colleagues and so on. So that is the so what do we have about fundamental particles that Uday was asking? That we have a list of particles that we have seen that cannot be split any further. They have certain properties that we know of, and we have a theory that up to certain energy scale, as I said, that to go to smaller and smaller length scales, you need to go to larger and larger energy scales. Of course, we have some physical limitations in here. Both in terms of space, finances, and technology. So far, our most energetic collider is planned to go up to about 14 tera electron volt of center of mass energy. Will be upgraded again to about order. So we have around 14 tera electron volt of energy scale. That is the energy frontier as of today. Of course, it's going to get upgraded by 2030. We'll have a bit more, but when we will go another order of magnitude higher, we do not know yet. So, but the point is, so up to that kind of energy, this is the model. That's what I want to say. That if you so in terms of length scale, basically, if you see my previous chart, we are somewhere around in here. So these are the particle contents, and we have the charge. We know some of the quantum properties and how they interact, how they talk to each other. We have a model for that. Yeah, thanks to many hardworking scientists and many geniuses. Yeah, as you see here. So this is what we know. This is the fundamental building block. Now, if all of these are fundamental, the question actually also said that Uday is probably mostly curious about what we are made of. If all of these are fundamental, why don't we see all of them? I mean, we have never encountered atom that has a muon in it or that has a tau1 in it instead of electron. In spite of muon and tau1 having same charge, they are heavier in terms of mass, but you see spin and charge, they are the same. In fact, yeah. So these quarks and leptons, they kind of appear in families. So along each vertical line, the properties, they mimic one another, just that each of them are heavier compared to the ones that are appearing to the left. So that's how it goes. And here are some examples of decay processes. As I said, that our model also says that the heavier particles should decay to lighter particles via whatever processes that are allowed. This one is a muon. Muon actually decays to an electron antineutrino, and a muon neutrino. And this diagram goes by the name of Richard Feynman, known as Feynman diagram. This goes by the name of that, and one can actually calculate. So each diagram, I'm not showing the expression, but each diagram corresponds to some calculation. One can calculate the probability of this process happening, or rate of process happening. One can calculate and one can measure. That's how we gain confidence on the theory that we have. This is a decay diagram for the Higgs boson that has a mass of 125 GeV. You know that mass is equivalent to energy from Einstein has taught us, right? E equals to mc square. So in particle physics, we use the convention, we tell the masses in units of energy, not in kilogram or not in grams, but just in unit of energy. And if you want to convert back and forth, you can divide by c square. That is the idea. So here, if you see, Higgs mass is written as some 125 GeV over c square, like that. So these are the kind of, so our model tells us that there are certain, I mean, we have a collection of particles that has certain charges and certain quantum charges, and then we have a model for their interactions. Those interactions tell us how they talk to each other, or whether they are stable or not, most importantly, because let us focus on the stable particle zoo for a moment. So quarks are not found freely for something called confinement. And let me note the technicalities, but they form hadrons together at low energies. So hadrons come in two forms, baryons and mesons. They are held together. So these hadrons are held together by strong interaction, which is mediated by gluon, yeah, that we already talked about. The lightest of the baryon has nowhere to go. This particle is stable. This is the proton. Yeah, baryons are made of 3 quarks. Yeah. Proton, as you know, is up, up, down. So lightest baryon is proton, and this particle is stable. Now, neutron, although you have seen neutrons being, staying inside the nuclei, free neutron, however, actually decays to a proton and an electron and an electron antineutrino. This decay, you have read about beta decay, I believe, at least those of you who are in high school, you know that weak interaction mediates this decay. So a free neutron would decay inside a nuclei, neutron, proton, they interact inside a stable nuclei, neutrons stay as they are because of certain interest. So neutron has a lifetime of about 880 seconds. I'm mentioning these two particular baryons because proton itself is stable, neutron is not stable, but inside a stable nuclei, neutron number stays the same. Okay. Inside unstable nuclei, of course, neutrons can beta decay, and you have the nuclear transitions because of that. In the charged lepton sector, electron is the lightest one. This is also stable. Why is it important to be stable? Because if this guy is not stable, how would it form anything, right? Even if it is a fundamental particle, does not necessarily mean that it's going to participate in the formation of an atom or a nuclei, right? This guy has to be stable in order to do so. It should not be decaying. So lightest charge lepton, that is electron, that is also stable. Photon is massless, of course, this is stable. Yeah. Note that a particle can only decay to something that has mass lesser than it, right? This is ensured by the energy conservation, some kind of energy conservation in the context of special relativity, if I may say so. Yeah. So photon is stable. So note that so far, although I'm talking only about particles, fundamental particles, as the topic is suggested, but proton and electron, these guys, actually all the members that you see here, they also have antiparticles. For some, they are their own antiparticles. I mean, they don't have their antiparticle is the same particle. But let us talk about the stable particles, that is proton and electron, for example. They have a corresponding stable antiparticle as well. Now, if that is there, then why don't we see it? Now, this is another big question, how this asymmetry between particle and antiparticle was generated. And but just keep in mind, this is another exciting question to think about. The theory that we have, which we believe is extremely accurate to energies up to about several TeVs, tens of TeVs at least, very accurately predicts the this predicts that there should be antiparticles for each particle. This was actually known since Dirac's time. If you have seen, if you have heard of Dirac, he had an equation for this so-called fermions, the spin half guys. He had an equation for them. That equation makes a prediction for antiparticle, and positron was predicted then. So one question to keep in mind is, the theory has antiparticles in them that have the same properties, except for the charges would be opposite. Photon does not have an antiparticle. I mean, it's in other term, it's its own antiparticle, we would say so. So is Z, W plus minus is one another's antiparticle, and so on. But for stable particles, you can see proton and electron would have an antiparticle. Now, there is another particle that I would like to briefly talk about. I don't know if I'm running very slow. This is neutrino, because I was asked about this does not make anything as such, but this is there. This is also stable. We know very little of them because this interacts very little. And this you can see, it produces, it is produced a lot in the atmosphere because cosmic rays, high energy cosmic rays would come and hit atmosphere. This produces something called pion in the process, in the hard scattering. The pions, the charged pions, they decay to muons, and then muon flavored neutrinos and antineutrinos there. So a lot of such muon neutrinos are produced in the atmosphere. In sun we know is generating energy for all of us, and we're very grateful for that. But in sun there is this process that proton fuses, and then you have deuterium plus positron and an electron neutrino. So electron neutrinos are produced in sun, and they stream all the way to Earth. Now, many solar neutrinos pass through us every second, but this is weak interaction that they have, and we can compute the rates. None of them interact, and we don't feel them. They are just passing through us. By many, you have not put the numbers, but they should be order 100 billions or so, roughly speaking. Now, these neutrinos are detected by dedicated neutrino detectors. So that's a separate story, and maybe I would just skip through it because I really think I'm taking longer. This is a detector called Supercomputing in Japan, and this is a detector called Ice Cube. This is a Cherenkov detectors, huge size, as you can see in the scale about. And these detects neutrinos through something called a charge current interaction. And these interactions are very well calculated within the model we have, so we know what to look for. But anyway, coming to the last part, that protons and neutrons, they together make nuclei, and this nuclei is inside the nuclei, protons and neutrons together are held together by something called this residual strong force, by meson exchange. Then nucleus binds electrons, forming atoms, and then atoms join together to form molecules, and we have the entire hierarchy. From there, we can go up in scale. Now, how do we see the heavier particles? Through experiments. And here I would just, this is one picture of the CMS detector, an event in the CMS detector, compact muon solenoid at LHC, Large Hadron Collider. Yeah. So you have, as I said, that in order to produce heavier particles, we need more energy. So this collider, what does it do? It accelerates protons to very, very, very high velocity, very, very high speed, pretty much close to the speed of light. So it's like some 0.9999 times speed of light. Or, yeah, and then that carries, proton has a rest mass of 1 around 940 GeV. So then its mass goes, I mean, when you accelerate to that kind of high energy, those of you who have learned some special relativity, you know the gamma factor that comes in the special relativity, the energy is much more, that proton is carrying much more energy. So it just collides bunches of protons inside the collider. Now, if it has more energy, we can calculate again using our model that Dr. Kenji Nishiwaki will talk about in a moment, what would be the rate of production of the heavier particles, and then those particles, we know exactly where they decay and we know what to look for. It is still a challenging job in terms of data analysis and so on, because huge number of collisions per second is happening inside the detectors, and we have to isolate the right events. But that's how we identify the existence of the heavier and the heavier particles, the ones that decay that we don't see in forming atoms or something, but we know that they are there. The other thing is it's a slightly older technique using cloud chamber or bubble chamber. In fact, this picture I get from Wikipedia. This is by Anderson, around 1932 or so, first image of positron in a cloud chamber. So we can talk about it later. But this comes from the cosmic rays in this case, and it's detected by the cloud chamber. Anyway, so that's how we know that the heavier guys are also there. The heavier fundamental guys are also there that do not participate in atom formation. Okay, yeah. So that's about it for the first question. Thanks. Over to Uday.
Oh, thank you so much, sir, for the insightful.
Sorry.
So, for continuing from here, I would like to ask Dr. Kenji the next question. Sir, could you elaborate a little more on the standard model and what are the different types of particles that Dr. Rindam talked about? And why is the Higgs boson known as the God particle?
Okay, my side. Okay, please wait, and I start to share my screen. Wait. Okay. Where is, sorry. Open. You can see?
Yes, sir, we can see your screen.
Okay, fine. Yeah, okay. So, yeah, okay, let me continue the session. Yeah, okay. Again, and thanks for very kind invitation for me and to this nice program. Yeah, the second question I received is, what is a standard model? And what are the different types of particles that are included in it? And what is a Higgs boson, and why is it called the God particle? This is, I try to answer this question step by step. Okay. Yeah, Dr. Arindam Chatterjee already kindly introduced the basic part, but very briefly I'm talking about. Yeah, we know, and our, yeah, how to say, atom, yeah, it consists of the nucleus, the very heavy center part, and the circulating electrons. Of course, when we change the number of the electrons, it corresponds to the different matters, one by one. But first, we find that human being find that the center part consists of proton and neutron. Yeah, this is the very magnificent, yeah, discovery of the fundamental structure of our materials. But scientists find the substructure. Yeah. So this proton and neutron consist of up and down, two different kind of quarks each other. The numbers are different because proton has non-zero electromagnetic charge, but neutron is not. Then the contents of the quarks should be different. But two from up and down quarks, we can explain the more basic origin of the proton and neutron. Yeah, of course, such substructure should correspond to a shorter length scale. Shorter length scale, as Dr. Arindam explained, correspond to the higher energy. Yeah, so such structure is firstly and theoretically postulated. But now, such a structure was completely confirmed and described by the standard model in the particle physics. This is proposed in the first idea in the 1960s, and the one magnificent recent event, recent but almost 10 years ago, but in July 2012, yeah, CERN find the last missing piece of the standard model called Higgs boson. Okay, so talk to this, yeah, maybe, and I introduce one important concept, very important concept in the particle physics and quantum physics. This is spin. Yeah, this is very important quantum number. Yeah, so when we try to consider such kind of material, of course, this is a mock-up, this is not the real thing, but when we consider that such a object, yeah, it's spinning, we can find the angular momentum vector of this spinning. Such important point is that for a pointless object in the quantum theory, we can consider such a spinning degrees of freedom for every particles. But interesting thing is that this is a very characteristic point of the quantum theory, that this theory cannot take continuous values. Yeah, we call this is a quantized. Quantized means, yeah, this is very close to the concept of digitized. Yeah, possible number is finite. For the fermion, plus 1/2 or minus 1/2 is allowed as a unit of the basic new unit described the quantum theory. This is called the Planck constant. Today, not much time to explain the detail of the quantum theory, but the point is that such a discretized spinning degree of freedom can be attached one by one in different particles. Yeah, we can easily check that such a nature is realized. Is that just we try to filter the electron and yeah, putting in such a very inhomogeneous magnetic field. Yeah, if such quantum number is not quantized, yeah, such a continuous distribution is expected. But reality is not. Only two dots. They corresponds to plus 1/2 or minus 1/2. Some two spots only observed. This is a definite evidence for such a quantization. In this case, the value of the spin. So this is the contents of the standard model. Dr. Arindam already explained. So of course, it should include the material for our atoms, up, down, and electron, up and down quarks and electrons. But there is another kind of fermion. Yeah, these are called the particle called fermions. Fermion is defined as a particle with spin 1/2. They are fundamental origin of our materials. weird points. One is, in addition to the first three classes, another particles, neutrino, is in nature. They are very, very light, but their mass is not considered to be exactly 0. The second weird point is that, in addition to the such a 4 particle, we can find 2 additional copies. Yeah, these copies, how to interact with others is very, very similar to the first ones, but they are much, much heavier than the first groups. But in any case, all of the particles are already probed by the experiment. And in addition to this, we should introduce another 2 particles. The first category is called gauge bosons. The last category is the Higgs bosons. I explain step by step. Of course, standard model is the model for describing the fundamental force observed and confirmed till now. Then it should contain a consistent way to describing the force exchange. This is a skeptical picture that if we consider, for example, if we exchange soccer balls, any balls or boomerangs, and we can mediate a force, both of the repulsive and attractive forces. Then mediation of the force corresponds to the exchange of the force. This is the basic idea in particle physics. The gauge bosons are such a force mediators. The first important force is, of course, electromagnetic force. Yeah, as widely known, the mediator, this mediator has spin 1, yeah, and called gauge bosons, and the photon is the electromagnetic force mediator. This is widely known. The W plus W minus boson, another kind of mediator, is necessary because we know that the beta decay, yeah, for example, yeah, free neutron can decay into proton and electron neutron, anti-electron neutrino. But of course, yeah, neutron has no electric charge. Then photon cannot describe such kind of decay. Then we need another kind of force mediators generating the beta decay. The last one, yeah, gluon. Yeah, this name is of course coming from the glue, because the strong force is acting between the proton and neutron. Yeah, this gluon glues these 2 particles consisting of the nucleus. Because without such a strong force, much stronger than the electromagnetic force, the repulsive force between the protons, yeah, devastating the structure of the nucleus. Then we can understand the necessity for this such strong force, yeah, working between the nuclei. This force, magnitude of this force is very, very different. Yeah, gravity is also a kind of important force, but the typical magnitude is much weaker than the other 3s. Then usually we do not care about this in the particle physics. So much. Finally, let me introduce the Higgs boson. Higgs boson has no spin, zero spin, then this particle cannot point any specific directions. But on the other hand, such spin zero particle called scalar can cover our universe by such a particle background, for example, like this. If our our universe, such kind of background, we can describe the magnitude of the masses of the particles as a strength of the coupling to this Higgs boson. Because if a particle coupling stronger than the others, it can be considered that this particle can hit such background more frequently. This is a schematic picture that heavier particle can be considered that it tend to hit the background, then it cannot move so fast. And this is interpreted as such a particle has a heavy mass. Okay, let me finally mention this statement. Higgs boson is the God particle. This statement first appeared in this popular book written by the Professor Leon Lederman. He is very well-known experimentalist, and he was entitled to the Nobel Prize in Physics 1988 for the discovery of the mu neutrino. I briefly introduced this one. Okay. In the title of this book, this popular book, this God particle appeared. So of course, Higgs boson is very important because without Higgs boson, we cannot describe the mass in particle physics appropriately. But on the other hand, of course, other particles are also very important. Then let me emphasize that this phrase is just kind of a phrase, non-scientific phrase. This phrase has no specific meaning in science. Then I found such another popular comment on this statement, and this is maybe more nicer. Okay, sorry, maybe I completely use my time slot. Okay, let me finish my first presentation here.
Thank you so much, sir. That was a very nice explanation. I would now like to move on to the next question. And as we are running short on time, I would request Dr. Arindam to give us a very brief answer. And I want to ask, what is dark matter and dark energy, and what impact does it have on our universe? Would our universe be any different if dark matter didn't exist?
Yeah, it would actually be very different as for our current understanding. Again, let me share the slides, and maybe I will just briefly go over it. The material seems to be too much for the one discussion indeed. So here is the dark matter slide. Just give me two minutes. So we have already discussed about a lot about particle physics, and so I guess we have been able to convey an idea that there are these particles and interactions. Dark matter is dark in the sense that it does not interact with photons, and there is nothing. How to say? There is nothing fishy about it. We have already seen some other particles in both. Were described by Dr. Kenji Nishuki and me in the beginning, that neutrinos, for example, are also neutral charge, and they don't have electromagnetic charge. They don't interact with photon. And Higgs boson is the other example. It does not decay. Higgs boson does decay. Neutrinos do not, at least the lightest neutrino should not decay. But Higgs is another example that does not interact with photons. So there is nothing fishy about it. Now, how do we know then these things exist? We got to see them somehow, right? So the evidence is again gravitational. Here you see there is something called a galaxy rotation curve. This is taken from this particular paper for a particular galaxy. This basically says how fast the external objects or external stellar or celestial objects in a galaxy, how fast they are moving. On this x-axis, it should be galaxy radius. And if you have done Newtonian gravity is enough to answer this question, and you know that is roughly half mv square by r, that is the centripetal acceleration, is provided by the gravitational force. Gravitational force is calculated by taking into account the mass that is enclosed within radius r. Now, if you do that, you would have an expectation just for the disk-like galaxies that the rotation curve should fall like this, but observation goes like that. Yeah, if you can see the screen. So the baryonic matters, the matters that scatter light, they cannot explain why the rotation curve looks like that. There's another thing called another measurement called mass to light ratio. Actually, dark matter, several evidences across cosmological scales from the large scales in the sky over megaparsecs to very, very, very small, like galactic scales, galaxy cluster scales, then galaxy scales. Everywhere we see evidences of missing mass. So this is another example of coma cluster that was observed even since 1930s. People know that mass to light ratio, like there is a way to estimate if certain the luminous mass of the galaxy. Yeah. So if you're getting certain amount of light, what should be the corresponding baryonic mass using virial theorem and measuring the temperature of the photons that are coming towards us. So there is a way to estimate the mass to light ratio. And for coma cluster, for example, it was known since 1930s or so that there is a huge excess in mass compared to what light is being received. So there is a discrepancy in the mass to light. So galaxy rotation curve in galaxies, mass to light ratio in clusters. This is a lensing picture. Here you can see that this, I don't know if you can see, this is a Hubble image of a massive galaxy cluster, and the background galaxies here are lensed. If you can see this, how to say, elongated lines, see as circular thing in the image. Probably you see it better here. This is gravitational lensing. So this is used to routinely estimate local gravitational fields. And this cluster, if you map, so this is the visible thing that is coming from the cluster. And if you map the gravitational field using the lensing, you get the mass distribution as this. So there is clearly extra matter. This is a simulated thing, a mapped thing, and then you just put like this whitish foreground as distributed mass, where you expect mass should be there, but that mass is not luminous. So this is also again lensing of Hubble, and this is a well-known bullet cluster. Maybe I'll explain sometime later. But and this is something called, this is the oldest light that we can see today. This is called cosmic microwave background radiation, and isotropy in that the radiation has a temperature of 2.73 Kelvin and with an anisotropy of about order 10 delta T over T 10 power minus 4 or so. So this is in hundreds of microkelvin. So there is small temperature isotropies. This also tells us, I'll not get into detail, but this also tells us that there should be sizable amount of matter that is not scattering light, that is dark. Okay, and how much? And this is the current estimate. This is by Planck collaboration. They, I think, finished their data taking in 2012. This analysis is a 2018 analysis, but the numbers are about similar. So this is the, if you think of this pie chart as universe's energy budget, then dark matter constitutes, so matter altogether constitutes about, as you can see here, 30%. Ordinary matter happens to be only about 4.9% or so, 4.5, 4.9%, and then dark matter is about 26.80%. And this is rest is something called dark energy. So as you see that as for our understanding, there is more matter that is dark matter compared to all the standard model particles that, I mean, all the matter that we know in the standard model, all these particles that we describe now. Is there a candidate of dark matter in the standard model? The answer, unfortunately, happens to be no. There is no particle candidate. Anyway, so I think I would just skip the rest of the things. Now, another question that I would like to touch upon is what would happen if there is no dark matter. To here, in order to describe that, look at so this is another standard model prediction. This is standard model of cosmology known as lambda CDM. Lambda stands for cosmological constant. CDM stands for cold dark matter. Like we had standard model of particle physics, this is standard model of cosmology. Now, you see here that according to this model, the universe was very hot earlier, and then gradually, this is where the CMB photons, very, very old, about 13 billion years or so old photons that are streaming to us. Now here you see that there is no structure, no galaxy, no planet. Forget planet. There is no galaxy, no star, nothing in here. Here everything is a hot plasma. Now, dark matter actually happens to help structure formation, and the galaxies, the stars, the planets, all that we see, the structures are in order for the structures to form. It so happens that we actually need dark matter. This part is a bit tricky. One has to do some simulations, and there are large-scale simulations in there, but basic physical arguments in terms of Newtonian gravity suffices to explain that. So if there is no dark matter as of our current understanding of the universe, if you were to explain CMB, you would struggle to explain that, the cosmic microwave background anisotropies. And in our current understanding of cosmology, structures would not form if there is no dark matter. At least not so many structures that we see today, they would not form in the evolution of time. Dark energy, however, does not clump. It is not like matter, since the question also had a bit on dark energy. It's very interesting physics, but again, we have no time. So I would just say that cosmological constant is the simplest model for dark energy. The motivation is the Supernova Cosmology Project and High-Z Cosmology Search Team in 1998. They measured the distant supernovae, the light coming from that. Now, using Einstein's equations and within so-called Friedman-Robertson-Walker cosmology, one can exactly calculate, like if light is coming from supernovae, whether the light coming from the farthest, the farther supernovae should be fainter or brighter, or how should it go? Yeah, so it so happens that these teams, by observing supernovae, the light they are receiving, supernovae are standardizable candles. Type 1 is supernovae specifically. These are all type 1 is that are shown in the plot. Plot is taken from this particular paper on arXiv. Anyway, the point is that you see how much light you get, and you see the redshift of the light, because we know that distant supernovae are moving away from each other. Now, by looking at the redshift, and even in Doppler shift, I think we have studied that if some object is moving away or coming towards us, the frequencies do shift, right? So here the reason is different, but you have similar redshifts, because for this supernovae, we know are moving away from us for sure. Yeah. Now the question is whether they're accelerating or no. And then by looking at carefully the distance modulus versus redshift, or the observed luminosity versus redshift of the light, one can figure out that the universe is not only expanding, but expanding in an accelerated way. Now, this requires, in standard cosmology, introduction of the so-called cosmological constant or dark energy. Without that, this would not be possible. Now, I would stop in here, and maybe in this short time, it's very hard to get in more detail. But yeah, so if there is no dark matter, structure formation would be difficult. Even if you forget about CMB, in standard cosmological model, within reasonable assumptions, you don't form so many structures. So many structures would not form. And if dark energy is not there, then this distant supernovae, this particular data, that distance redshift data for from further for the supernovae observations, we would not be able to fit it. We don't know how to explain it then. That's it. Okay. Thank you.
Thank you so much, sir, for that answer. For the last question, I would like to ask my question for Dr. Kenji. And so, like in recent times, we have heard about the possibility of there being a fifth force in nature. Also, since a lot of students on YouTube have been asking about this question, so what does this possibility really imply? And what are the particle physicists doing to know more about this new force? Sir, could you please answer?
Okay, yeah, please let me start to share the screen again. Where? No. Oh. You can see it's okay. Okay, let me answer my second question, and this is in recent years, we heard about the possibility of there being a fifth force in nature. What does this possibility really imply, and what the particle physicists are going to know more about this new science? Okay, so okay, let me introduce this one. Many physicists also many people are very now interested in this news. This is the press release from the Fermilab. The Fermilab is a very famous laboratory in US. Okay, the first result from Fermilab's muon G-2 experiment strengthens evidence of new physics. And this appeared in April 7 this year. And soon after this, many such popular articles to explain some detail of this. So here, two important keywords. First is muon G-2. The second one is a new physics or unknown particles. Okay, let me briefly introduce this concept. New physics or unknown particles, the sense of this is very not so difficult to understand that this is the structure beyond the standard model. In the last session, I very briefly introduced what is the standard model. Standard model is to describe the confirmed three known forces in nature. But there is no reason there is another force and or another particles in the universe. And as Dr. Arina introduced kindly, that we have lots of motivations to consider such an extended structure. For example, there is no dark matter candidate in the standard model. So, but here we try to focus on the second one, muon G-2. In the previous session, I introduced very briefly the spin. This is the intrinsic, precisely speaking, quantized angular momentum vector of elementary particles. Muon is an elementary particle. And the point is that what is the overall strength of this spin angular momentum of the muon? Other parts are known from the discussion in the quantum mechanics, but the overall structure is almost equal to 2. But there is, after taking into account the quantum effect, this overall magnitude G is slightly deviated from the classical variable 2. So point is, if so, okay, but how to measure this small deviation from 2? Here, when we consider the variable G minus 2, 2 is of course this classical variable. This is a good parameterization to parameterizing this quantum part. Then of course, after taking into account the quantum effect, the overall magnitude is a bit modified. Then of course it can affect the phenomenon. So here we are talking and focusing about this phenomena precision. Both in Earth or top, they are spinning. Of course, they have finite structures, but this analogy is very powerful to understand what we would like to do or what experimentation phenomena did in the experiment. Yeah, if objects are spinning, there is an angular vector, and after considering the gravitational force, this axis pointing the spinning direction is rotating like this. This is called precisions. You can easily check this phenomena by use of a top immediately. But the muon has a similar such kind of polarization axis or the spin. Then we can do a similar thing. But this time, yeah, we cannot use the gravitational force because muon is very light. But instead, we can use the magnetic field. Because fortunately, muon is electromagnetically charged. Then by use of this, yeah, we can measure such a precision of the muon's spin vector under the magnetic field. Yeah, to very carefully, measure this precision. Yeah, there's a very nice lecture on the YouTube, and all the details. Yeah, please kindly check this movie, this online lecture. But but the idea or a schematic picture is very easy to be understood. If the overall magnitude is exactly equal to, we can show that if we putting the muon in such a ring, then after a rotation, the direction of the momentum and the spin is completely parallel each other in each step. But if additional correction is there, spin receive additional kicks, additional rotation around the circulation. Then after one circulation, the two vectors are not parallel each other. We can measure this difference and getting the corresponding value of the experiment, A mu. This is G minus 2 over 2. This over 2 is just a factor. The important point is we consider G minus classical value 2. So, of course, this value is measured by experiment. But by use of the theory, of course, the theory is a standard model, we can calculate the prediction for this value. Yeah, here is the difference between the latest experimental value and the latest one of the latest theoretical value. Yeah, this is amazingly agree to each other. Please, consider that G is 2, then the first order is just order 1. But this difference is, roughly speaking, 10 to the minus 10. Yeah. Up to 8 to 9. Yeah, like such a first 8 digit, for example. Yeah, the experiment and the theory prediction are completely agree to each other. This is extremely amazing achievement in science. On the other hand, but yeah, story continues. But some difference. This difference is very typically this magnitude. Yeah, that's the very small difference. But this difference corresponds to 4.9 sigma in the statistical sense. Yeah, this green band shows the central value of the theory and 1 sigma error of them. Yeah, this red point and the bar corresponds to the central and 1 sigma error of the latest experimental result, and combining the latest and the previous experimental result by the another experimental group, roughly 10 years before. This is the latest, combined result of the experiments. 4.2 sigma deviation. It's not small. Here I quoted the very nice table from the Wikipedia that, of course, everything can happen accidentally, in principle. For example, when I type my keyboard randomly, of course, there is not the probability I can write, for example, Harry Potter series. This probability not exactly 0, but extremely close to the 0. So then this sigma, corresponds to the how, if such deviation is just by accident, how likely or how unlikely such a confidence level tells us. 4.2 sigma is as the rate for the daily event. This 4.2 sigma event appears once in maybe a lifetime of people. It can be considered very rare. Then, many physicists can be has a strong interest on this result. Another important point is that the latest result tend to very similar to the previous result. Then maybe both will be the true. I'm not sure, but this 4.2 sigma is not so common. Okay. Of course, next what we should do is that what is the origin of the difference? Precisely speaking, what is the possible origin of the disagreement? Of course, one possibility is that if there is a new physics in our universe, in addition to the standard model, the new physics part can contribute to this variable. So, of course, there is lots of ways to address this discrepancy. Then, if this deviation is completely confirmed, both the theory side and the experimental side, completely means very precisely and confirmed, and then it can be a indirect evidence of the new physics structure beyond the standard model. Interestingly, till yesterday, more than 100 papers, manuscripts are published on the internet on this possibility. The second possibility is that, the standard model, theory calculation has maybe has a bit subtle point still, because this is the standard result or the standard model expectation, but part of the effect includes the hadron exchange. As we discussed, hadron is strongly interacted. Then calculation of this contribution is not so easy. This group evaluated this part by use of a different method. And they claim that the central value of the standard model is not here and here. There is some room to be clarified within the standard model calculation also. This is another possible origin of addressing this discrepancy. Third point is that, of course, how precisely or how accurately the experimental result is. Of course, this is also a possible issue. But the latest result from the Fermilab, based on this talk, they still has a lot of unpublished data, and the updated result with the more data will be clarify the precise nature of this muon G-2 in the near future. Then, then my comment on this question is that maybe more discussions, analysis, data seems to be necessary to answer this question appropriately. But this subject is very interesting because many theoretical part and of course very, very precise experimental issues are addressed from the many different point of views. Our message is that to confirm a new phenomena is not so easy, and we have more time and effort. Okay, let me finish my answering part, or the second part. Sorry, I cannot hear you. Sorry.
Vinita ma'am, we aren't able to hear you. Ma'am, we still can't hear you. Yeah. Okay. Thank you, ma'am. Thank you for that note. I think we'll be taking a few audience questions now. As we're running a little low on time, we won't be able to take all of the questions as of now, but please note that during the summer session that we'll talk more about later, all the audience questions that we have received on YouTube will be catered to and hopefully be answered over the course of the next month. And I would now like to take up one audience question from YouTube. And this question is from Piyush Rajput, and he asked, is there a deeper fundamental property of neutrino oscillations? Dr. Arindam, if you could take that question very briefly, that would be great.
Sorry, what is the question? Could you repeat again?
Sure. So Piyush asked, is there
No, your voice is still muffled a bit. I could not hear.
Oh, okay. Once more. Am I audible now?
Yes, yes.
So asked, is there a deeper fundamental property of neutrino oscillations?
I'm not sure what exactly you mean by a deeper fundamental property, but generically speaking, neutrino oscillations, that is neutrinos that emit from the source as one flavor, when you detect them, you might detect them usually by a charge current interaction. You see that you are obtaining another flavor. Typically, this oscillation is attributed to a small mass difference between neutrino mass eigenstates. So the flavor eigenstates and the mass eigenstates for the neutrino, meaning like muon, electron, and tau flavored neutrinos, these are the flavor eigenstates. They participate in the interactions like that. But when they propagate, it's usually a mixture of all three of them. That's what constitutes a specific mass eigenstate. And there are small mass differences of delta m square. We do not know exactly neutrino mass, but delta m square's values are measured from the neutrino oscillation properties. And we quite accurately know at least two of them very well. So that's what the oscillations are attributed to, and so far it's a good fit to the data. Yeah, I do not know what you mean by more fundamental property, though. What do you mean by that? But oscillation, in our view, is well understood in terms of tiny mass differences between the mass eigenstates, and the fact that mass eigenstates are composed of multiple flavor eigenstates, where yeah, these three neutrinos mix together, three gauge eigenstates, they mix together. Okay. Thank you.
Thank you so much. Can you all hear me?
Yes, we can hear you.
Thank you so much. So time is less, and it was such a beautiful session. And I can see a kind of bonding between students of college and school, because on YouTube there is a student from SNU, Partho, who is continuously taking questions of school kids and replying with such a passion. And it is so overwhelming to see that, peer tutoring, a kind of peer tutoring is happening on live YouTube channel. And the whole purpose of asking college students and many more to join on YouTube, so that there are many questions, Dr. Arindam, there are many questions, Dr. Kenji. Time is very less. So I am expecting Uday and Devangi. Please take it forward, and please do announcement of what is there for all these kids who are so eagerly posting on YouTube chat box.
Yes, ma'am. I will talk about that. So I hope everybody enjoyed the session, and thank you for attending. So we would be starting a peer tutoring session for particle physics. So Panther, then I would be taking these sessions in collaboration with Nucleus team under guidance of Dr. Kenji and Dr. Arindam. And we would be circulating a Google form. So whoever is interested is kindly requested to fill the form, and then we will update you soon about the session.
Yeah. Also, Devangi, this is very important to share that. Uday, will you please show the slides one by one? So all the queries will be made clear in summer break, and maybe two sessions in 1 week will be taken by Uday, who is a passionate physics astrophysicist and particle physicist himself, and Devangi. And obviously, we cannot, we cannot forget Partho, who is continuously replying queries on YouTube. So over to you, Uday.
Right, thank you. Right, so as Devangi said, we'll be starting a month-long summer program known as Fundamentals of Particle Physics, which is basically an extension of this session that we had today. And I hope that a lot of you felt inspired to take the journey of learning particle physics forward by joining us in this program. So we'll be collaborating with students from Shiv Nadar School and Shiv Nadar University under the guidance of teachers and professors from both institutions, and devising a module for all of you to tell you more about particle physics. We'll be using different simulations and animations to cover a large set of topics. And basically, we would be taking a deeper dive into the topics that we looked at some extent today. And another advantage of participating in this module is that you'll also receive an official certification after you complete the course. So you have something to show to other people that you can tell them that you have studied particle physics as a student. Now,
most importantly, Uday, I just want to add one line in continuation. That program anchor are Rachna ma'am for this particular program, and Manoj Kathuria sir along with me, because to bring all these queries to the school level, it's very, very important that school teachers also take ownership. So Manoj Kathuria sir is a passionate physics teacher, and Rachna Arora ma'am are physics HOD from SNS Noida, and Manoj sir from Gurgaon. Both will be also anchoring this and will be mentoring all sessions which you will discuss with them. Over to you there. Thank you.
Yes. So the program is scheduled to start on 1st June of 2021. So that's about a week and a few days from now. And the total duration of the course would be 1 month. And we would be having around 2 sessions per week, which would last 1 hour each. And during each session, we'll be covering something new, something different. And it'll basically take you from knowing the basics of particle physics in the early sessions to slightly more complicated topics by the end. And we would try to make sure that you have a proper passage to go from just understanding the fundamentals to understanding where the future potential for particle physics lies in the future. We would also give you some minor tasks and assignments so you can stay engaged throughout your summer vacation. Now, you can register for this program using the link that is shown on the screen right now. The same link is available in the description of this YouTube live stream as well, so you can have a look directly on the same web page that you're on right now. And the form will also be available on the Nucleus website pretty soon. So if you're not able to access it through YouTube for some reason, you can also access it using the Nucleus website. And the last day to register for this program is 27th May. So I hope a lot of you do register and join us on this program, join me and my peers, and I hope we have a good time. The sessions will be conducted by me, Devangi and Pantho, under the guidance of Ms. Rachna Arora and Mr. Manoj Kathuria, and of course, Vinita ma'am as well. And we will also be taking help from our speakers today, Dr. Arindam and Dr. Kenji, in order to give you a well-informed experience and a well-informed course about particle physics. So again, I'll repeat, the link to register is in the description of the YouTube live stream right now. You can register for free, and we hope to see you on 1st June. Thank you. Thank you so much.
May I request Kabir to speak for a minute about our next program before Uday wind up the program? Kabir, over to you.
So Team Nucleus would be organizing another event on Environmental Day with Mr. Ezra on 5th June. The program anchors for the event will be Manoj sir and Vinny ma'am, and we are all looking for your participation. Thank you.
So this World Environment Day, we are going to also invite some students who have done something for sustainable world and sustainable development. So in that, there are 2 students from SNS Noida. One is Raghav, and Mathur and his brother will be taking 1 or 2 sessions also, along with how to bring use the waste material to make things. So I hope you all will join us on 5th June. Over to you, Uday.
Thank you so much, ma'am. I think that brings us to the end of this event. Thank you so much, everyone, for joining us this evening and tuning in to learn more about particle physics. I think it is really important to study these more abstract fields of academia as we go on, as the world progresses into a largely scientific environment, and as more people become interested in research, the idea of human development would just amplify in the future. Vinita ma'am, would you like to add your thoughts to the same?
Yeah, I would like to invite Rachna ma'am to share vote of thanks because it's 10:30. And yes, Dr. Arindam and Dr. Kenji, just one line from my side. Uh, we are blessed. We are blessed to have such organization which has given liberty. I remember when I approached you directly, without any other SNU, teacher or student, I directly approached you, and the way you took it very positively. Words are not enough. And over to you, Rachna ma'am, please.
Yeah, Dr. Kenji and Dr. Arindam, thank you so much for taking the time to speak to us today on this very fascinating topic and for demystifying particle physics for us. I think all of us would agree that the session was very insightful, stimulating, and enthralling, and it will surely encourage many of our children to pursue the field of particle physics. You never know, maybe the next solution to the big mystery of the universe, it will be unraveled by one of our children who has been inspired by your talk today. So, sir, thank you once again, and we look forward to many such interactions in future too.
Yeah, we also thank to a big thank you to Devangi. She was having exam, so she was completely unaware that what Uday is planning and how I was approaching to these professors. And she passionately came and said, "Ma'am, can I join after 20th?" So yes, a big thank you to Devangi for showing keen interest in this. And the moment exam was over, she came and she joined hands with Uday. Uday had prepared everything, and so smoothly Devangi, and with a good bonding with a school student Uday, who is also now going to join Georgia Tech for physics this July. And both of them, along with Sambhavi, another very bright kid from Sitapur, whom I can't forget. She was the winner of EBC. Her speaker was not working, so she could not speak more. So a big thank you to this trio. Well done, kids. And also to Naman and Kabir, continuously staying for and solving all our technical glitches, and making teaser video, helping in all this thing. Thank you to Gulfam sir to always stand by nucleus and always spread all these sessions and with all the friends and all the students. A big thank you to Mayank sir, Ruchi ma'am, Megha Bora ma'am, Anamika ma'am, Karishma ma'am, and Manoj Kathuria, Sakshi Ganotra ma'am, Vinny ma'am, yes, of course, for all support. And a big thank you to my organization, Shashi ma'am, Matthew sir, and obviously Anju ma'am, Roop Manjri ma'am. I was on chat with her, and she said, Vinita, I am taking time to recover, so I cannot come, but my good wishes are there. So this is a great organization where I can approach directly to Vice Chancellor of University also. So thanks once again, everyone. Can I have a picture of Dr. Arindam, Dr. Kenji with our 3 stars, Uday, Sambhavi, and Devangi on screen? Just one picture. So will you please switch on your video? Thank you.
Okay.
Devangi, Uday, and Sambhavi, Dr. Kenji, and Dr. Arindam. Can we have all of you on the screen, please? Thank you.
Yes, I think everyone should be visible now.
Okay, so can you please just take a screenshot?
Yeah, sure. Yes, it's done. Thank you so much.
Okay, over to you, Uday. So you can close the session.
Yes, thank you. Thank you again, everyone, for joining us this evening. And I hope you had a good time. And I hope a lot of you register for the summer program as well. We hope that you go back to bed this evening and think a little bit about what such a strange universe that we live in, and have inquiries about the subject that lead you to research a bit more about particle physics. Again, thank you so much for our speakers and for the Team Nucleus for your support in organizing this session. And I hope you have a great week ahead, and stay safe during these unprecedented times. Thank you so much.
Can I just ask one question to Dr. Arindam and Dr. Kenji? How was your feeling, and how did you feel about this program when you are educating a mass right from grade 6 to 12 to college level students? So just any of you can speak about it.
So, yeah, of course, today I skipped to any specific detail of the mathematical side. But it would be nice to just provide some aspect of the particle physics, yeah, as a general audiences, with some, like this. Yeah, thank you.
Thank you so much, and we are looking forward for any kind of help you provide, sir. Dr. Arindam, would you like to speak last line before we close the session?
Yeah, thanks a lot to the organizers for giving us this opportunity to share some of the excitements in particle and astroparticle physics, and thanks to Kenji also, who accepted my request to join this session. And thanks a lot to the audience, of course, for whom the session is meant to be, like the curious students. And of course, we are also students, a bit senior, we are still learning, but it was a very enjoyable session. I have never done this before for school students, but it was a very enjoyable session. Thanks a lot.
Thank you. Over to you, Devangi, to close the session.
Thank you, ma'am. I would like to thank Dr. Arindam and Dr. Kenji for spending some time with us. It was a very insightful session, and I would like to thank everyone who attended today. So thank you, everyone.
So, Naman, you can close the live streaming. And